It's a pleasure to introduce Bruno Klingler from Humboldt University of Berlin. He's going to speak about on the algebraicity of the Hodge locus.
Okay, so first of all, I would like to thank Payman for the kind invitation to talk here. Okay, so I will talk about the algebraicity of the Hodge locus, and so this is essentially joint work with Greg Baldi and Emmanuel Ulmo. So let me recall a bit the motivation. So this will be, as you can imagine, essentially a talk in Hodge theory, but the motivation is a bit more general. And so you start with a smooth proper family of algebraic varieties of a field K. And then what you would like to understand is the fibers of these morphisms where you have exceptional algebraic cycles appearing in it. And the idea is that if you think motivically, the more algebraic cycles you have in the fiber, in some sense, the simplest the fiber is, right? So this is the motivation, and we would like to call this locus the motivic locus. And the idea is that you want to do this in family because essentially it's very difficult to work with a single algebraic variety. Usually, if you want to describe all the algebraic cycles in this single varieties, and this will be almost impossible most of the time. But what you would like to have is that maybe you cannot define exactly what happens on one fiber, but when when they vary, then maybe you can get the extra information that can happen in some fibers. So in this talk, the base field will always be C. And basically, we will replace algebraic cycles by Hodge classes. But before going to that, let me give some simple examples. So my family that I want to consider, the first example is a family of surfaces. So I fix D, an integer, and I look at all the surfaces of degree D in P3. Okay? And I look only at the smooth, sorry, it seems that I have a problem with my Siri. I look only at the smooth surfaces of degree D in P3. And so I denote by S the open of this big projective space that parameterize all the smooth surfaces of degree D in P3. And I take the universal family over S. So my morphism F is the universal surface of degree D in P3. So it's well known that if you take D at least 3, then such a general surface XS in this family will just have a Picard number, which is 1. In other words, you will have only a complete intersection in P3. But there is an exceptional locus, which is called the Noether-Lefschetz locus, which is exactly the set of points in your base S, where the Picard number is larger than 1. And if you work over C, then it's well known that this Noether-Lefschetz is actually dense in S. And when I say dense, it's not only dense for the Zariski topology, it's even dense for the analytic topology. Okay, so you have to think that in this universal family of surfaces, you have a lot of points that corresponds to the points where this Picard number becomes bigger, and actually this is dense. So this was one example. So I decided to start with an example which is less common than families of Euclidean variety, but now let's come to this. So example 2, which may be the simplest one, is you take the universal family of complex elliptic curves. Okay, so you would have to put a level structure different from SL to Z in order to have such a family, but nevertheless, so now my morphism F is from the universal elliptic curve E to the modular curve, and because I'm working over C, I just identify it with the affine line thanks to the J invariant. So the map is just to an element tau in the upper half space. It corresponds to the elliptic curve C mod Z plus tau Z as usual. And now the idea is that you can look at endomorphism of these elliptic curves, and as everybody knows, either this is Z, which is a generic case, or it's an order in Q of tau if tau is imaginary quadratic. And so this means that when I look at this family, so now there will be exceptional algebraic cycles that will appear exactly at the points where tau is imaginary quadratic. Okay, and so the special points will be exactly the CM points. So this will be the points in C of the form J of tau for tau imaginary quadratic in H. And again, of course, those points are dense. And the third example is just the generalization of this, where rather than looking at the universal family of elliptic curves, and I look at the universal family of principally polarized abelian variety of genus G. And there, again, the motivic locus is more, it exists, of course, and actually it is also dense, but it's more complicated. So I gave only 2 examples of this motivic locus. So you can look at the points in curved AG, which correspond to abelian variety with complex multiplications. So these are the CM points, and already those CM points are dense in that moduli space, even for the analytic topology. Okay. And another example is this subspace that I denoted by AGK, and this corresponds to the abelian varieties that splits non-trivially as a product of an abelian variety of dimension k times an abelian variety of dimension g minus k. Okay, and again, this locus is also dense. So we have at least 3 examples where we understand a bit what happens, and we see that this motivic locus is actually dense even for the analytic topology. So now I will restrict myself to really the Hodge incarnation of the problem about algebraic cycles. And so the idea is always the same. Rather than looking at the fiber of my morphism, I just look at its cohomology, and I can even fix a degree, for example, 2i. And I look at the Hodge theoretic gadget that I get this way. So if I take the fiber of my morphisms, then in terms as an abelian group, this is always the same. I mean, this is a locally constant sheaf, which is this V double bracket, which is this R2i F lower star Z. So this is a local system on the analytic space associated to S. But on each fiber, I have a Hodge structure. And so this is a notion of Z variation of Hodge structure on my base S. And rather than talking of the motivic locus for S, I will talk about the Hodge locus for V. So this Hodge locus that I denoted by HL as V tensor, this is the set of points S in S such that my Hodge structure at the point S has exceptional Hodge tensors. So not necessarily Hodge classes in VS itself, but maybe Hodge classes in some tensor powers of VS and of its dual. So this is a bit more general, right? All right, so
can I ask a question before you?
Sure, you're welcome.
So what exactly does exceptional mean? Like...
So okay, so what you can show is that you see, I mean, generically, the Hodge classes in a fiber will always be the same outside of a mega set on S. And so what I mean by exceptional, it means that it has more Hodge classes at that point S than in all the nearby fibers.
So it has more Hodge cycles than a generic.
Exactly, than a generic one. Okay.
Okay. Thanks.
Are there any other questions? As I said, I mean, I'm not used anymore to giving talks online, and so maybe I'm going just too fast. So if I'm going too fast, just tell me. I mean, this is really the context. So if you don't understand it, it's better to ask questions right now. Okay. No other questions? All right. So so the main player today will be this Hodge locus. And we have already seen some examples. The Nuttall-F-Schatz locus is included in the Hodge locus. The CM points for the moduli of abelian varieties are CM points for the Hodge structures, and so they are also in this Hodge locus, and so on and so forth. All right, so now what I want to do is to give a short reminder of Hodge theory, because maybe some people are not used so much with the description I want to use. So I just remind you what a Hodge structure is. So this is a Z module of finite type with a bigraded decomposition when you tensor by C. So the corresponding complex vector space VC is a sum of VPQs. And okay, the important condition is that VPQ bar is VQP. So this is just a linear algebra, semi-linear algebra gadget, if you want, over R. And equivalently, this Hodge decomposition can be described in terms of the Hodge filtration. So the Hodge filtration in the group P is the sum of those PCs VRS for all R larger than P. Okay, and then you pass from one to the other through the recipe that VPQ is FP intersected with FQ bar. All right, so the point which is interesting is that actually, I forgot to write this, sorry for that, is that this is the same thing as a representation of C star in GLVR, right? Giving yourself a bigraduation is the same thing as giving yourself a representation of C star cos C star. This will give you these PQs, right? Because the representation theory of C star cos C star is just by characters. So you decrete that when an element Z of C star cos C star, ZW of C star cos C star acts by Z to the P, W to the Qs, and this is VPQ, right? And the fact that you ask for this conjugation law means that actually the action is just the action descends to over R to an action of C star seen as a real algebraic group. So C star is really the restriction of scalars from C to R of the multiplicative group. So if I think this as a representation that I call X from C star to GLVR, then you can see that the Hodge classes, I can define them in three ways. Either these are the rational classes which are in the piece V00, or equivalently, these are the rational classes in F0, or equivalently, they are just the fixed point under this action of C star in VQ. Okay, so this is kind of a strange definition. You are comparing rational classes, the position of rational classes with respect to the Hodge filtration. So you are really comparing two natural algebraic structures which have nothing to do together. On the one hand, your rational lattice VZ or VQ, and then this purely holomorphic gadget, which is this Hodge filtration. Now, what is the main invariant of a Hodge structure? And this is the only invariant we will be actually interested in, is what is called the Mumford-Tate group for the Hodge structure. So what is the Mumford-Tate group? There are two equivalent, at least two or three, or even three equivalent definitions. So for people who like category theory, you can think that the category of Hodge structure is actually a Tannakan category. And then what I'm doing, I have my Hodge structure. I look at the smallest Tannakan subcategory of the category of Hodge structure generated by that one. And so the general Tannakan formalism will tell you that this is the category of representation of a certain Tanaka group, which is this group, G of VZ. So this is the categorical point of view. Another point of view, if you prefer, is just to think of my Hodge structure as a representation of C star. And then what I do is I take the image of that representation. So this is a subgroup of GLVR. But then I take the Zariski closure of a Q. So the smallest Q algebraic group that contains this image of C star. So this is an equivalent definition. And if you just want to think in terms of Hodge classes, this Mumford-Tate group, this is exactly the groups, the subgroup of GLVQ that fixes all the Hodge tensors in all the possible tensor power of VZ and its 0. So of course, these are all equivalent definitions, but they are just a bit different. So GLVQ is supposed to be a Q algebraic group. And I look at a representation of C star inside GLVR, right? So this is a real representation. C star is thought as a real algebraic group. So this is the restriction of scalars from C to R of GM, the multiplicative group. Does that answer your question? Yeah. Good. So if you want, you can just think that a Hodge structure, this is actually an algebraic group of a Q, this Mumford group, plus a representation of C star inside the real points of that group. That's another maybe more abstract point of view, but which is very useful. Okay, so now the standard fact of Hodge theory is that if you start with X, a smooth projective height over C, then I just recall you that its cohomology in degree I admits a factorial Hodge structure, which is more of a polarizable and which is of weight I. So I did not define what a polarization is, and I will not because it takes a lot of time and this is painful, but this is absolutely crucial for the theory. So this is a certain quadratic form or symplectic, depending on if the weight is even or odd, and which has certain positivity property. And because those positivity properties are a bit too boring to write, I decided not to write them, but this is absolutely crucial in the entire theory. And so the idea is that you want to construct a gadget that will encode those Hodge structures when you vary inside a family. And so this notion of variation of Hodge structure was invented by Griffiths in the 60s. So what is a Z variation of Hodge structure? Well, over a smooth quasi-projectivity S over C. So this is a local system over the complex analytic space defined by S of finite rank. Then you also give yourself an algebraic data, which is a holomorphic vector bundle curved V, a flat connection, and a filtration by holomorphic or algebraic subbundles, which satisfies the following crucial condition. So the filtration is not stable under the connection, but it satisfies this law. So you have to think that the filtration is decreasing. So FP is strictly contained in FP minus 1. So nabla does not preserve FP, but it maps it to the next rank in the filtration, which is FP minus 1. Okay. And this property is not for fun. It's just because Griffiths observed that this is exactly what happens for geometric families. And so, as I said below, the typical example, you have to think that you start with the smooth projective morphisms, and your local system is just the local system of the Betti cohomologies in degree 2p. Your holomorphic vector bundle is your push forward of your algebraic relative de Rham complex. Nabla, your connection is the Gauss-Malin connection. And the filtration that you get on this holomorphic vector bundle comes from the stupid filtration on the algebraic relative de Rham complex. Now, of course, what is the condition? Why is that related to Hodge theory? This is because you ask that these data at each point define a Hodge structure. So when you look at your local system at a point S, this is just a 1 abelian group. Then the filtration on this holomorphic vector bundle, which was analytic, VC tensor by the holomorphic function should be the analytification of that V. And so you want the filtration to define, you will get a filtration of the complex vector space associated to VZ at that point, okay? And the polarization should give you a polarization of the Hodge structure. So this is a lot of data to swallow if you never saw this definition. But actually, this is kind of very simple. Just have to think this is an object where you have a Betti incarnation, which is this local system, a de Rham incarnation, which is an algebraic vector bundle with a flat connection. The only additional data is this Hodge filtration. And of course, this is the crucial information. and this relation with the flat connection. Okay, other questions about that definition? So as I said, this is what you get for free in the geometric context. All right, so now let me repeat. So we were interested in the motivic locus, and now I replace motivic by Hodge locus. So what is the Hodge locus? So everywhere here, S should be S analytic. So I'm only looking at, if you want, close point on the algebraic variety S, but I prefer to think that I'm identifying S with its complex analytic space. Of course, this is completely forbidden, but let's do that for the purpose of that talk. So as a first definition, you just look at the point in S where the fiber ds, which is a Hodge structure, has exceptional Hodge tensors in the sense of the question that was asked a few slides ago. So I'm just looking at the points where I have more Hodge classes than in the fibers nearby. Okay. So another way of saying it is that you are looking at the point S in S where this group is not of maximal dimension. It is not generic. Actually, what Deligne proved is that this group is locally constant outside of a meager set. And you see that those two descriptions are the same because if I have more Hodge classes, then the group GS, which is the fixator of those Hodge classes, it becomes smaller. Okay. And so this is my Hodge locus, and you see that this is defined essentially in a completely transcendental way because the Hodge classes have to be rational, so they come from the Betti homology. And now I'm comparing the position of this Betti homology with respect to this Hodge filtration, which is an algebraic data. But this comparison is completely transcendental, right? Because I'm using identification of Betti homology with algebraic de Rham homology, if you want. So there is no reason why this set should have any good property. And what is remarkable is that you have this theorem of Catani-Deligne-Kaplan that tells you that actually this set has to be a countable union of irreducible algebraic subvarieties of S. Okay. So each time you have a variation of Hodge structure, you get for free this countable union in the base of irreducible algebraic subvarieties. And those irreducible algebraic subvarieties, I will call them the special subvarieties of S for the variation of Hodge structure. So, okay, so this is kind of a remarkable theorem. In fact, this answers a question of Weil. If you look at the last paper written by Weil in 1979, he observed that if you are in the geometric situation, so if your variation of Hodge structure comes from a morphism from X to S, then actually the Hodge conjecture implies this. The reason being that if you believe that any Hodge tensors correspond to an algebraic cycle in some power, so the algebraic cycles, because they are parameterized by some Hilbert scheme, it's easy to see that they glue into families. When they are exceptional, you would create a family of such exceptional algebraic subvarieties. But of course, this would be an algebraic family. So on the base, it will project onto an algebraic subvariety. So yeah, what will be important for later is that, so you have these general special subvarieties, a priori, well, you just have this theorem telling you that they exist. Usually they are difficult to describe, and even more difficult are those which are of dimension 0. These are the special points, right? I mean, it can happen that exceptional Hodge tensors appear only at one point. And so this means that one of those special subvarieties will be a point. And then inside those special points, you have those which are really minimal in the sense that their Mumford-Tate group is as small as possible. And so this means that this Mumford-Tate group has to be a torus. I should have said that because everything is polarized, this group GS is always a reductive group. So when it is minimal, it has to be a torus, actually. Okay. So you have this kind of hierarchy of special subvarieties. Okay, so now what I want to explain, what I'm interested in is trying to understand the distribution of those special subvarieties. What can we say about the geometry? I mean, this is kind of a really remarkable theorem. You start from a variation, and for free, you get a countable collection of subvarieties. What can you say about the geometry of that stuff? So we already have seen some examples, right? In the case of the modular curve, we have seen that the only special subvarieties are actually CM points. Right? In the modular space of abelian variety, we have seen example of special subvarieties. For example, those corresponding to a splitting of your abelian variety into a non-trivial product. This will define in the modular space some special subvarieties, and so on and so forth. But I'm not interested in describing each special subvariety, but rather, can I say something about their generic geometry? So to do that, rather than keeping this abstract description, I will use a standard tool also introduced by Griffiths, which is called period map for Hodge structures. So what is the idea? The idea is that, okay, you start with your variation of Hodge structure V over S. And this means that for each point S, you have a filtration essentially on a given fixed vector space, because don't forget that this is a local system. So this is locally constant, which means that around each point, I can identify the fibers at all nearby points canonically with the fiber at that point. Okay. So this means that essentially what I can do is I'm saying I go to the universal cover, then my local system becomes trivialized. And now the only thing that I want to describe is how the filtration moves on a fixed complex vector space. So this should give me a map from the universal cover to a certain flag variety. Okay. Now the polarization condition, which is crucial, tells you that you arrive in a certain holomorphic open holomorphic subdomain of your flag variety, which I denote by D. Okay. And now, because everything up to now is at the level of the universal cover, because of the monoromy of the local system, actually what I get is a map from the analytic space of S to the quotient D mod gamma. So here I have to explain a bit the structure of the object so that you are not too much lost. So in the case of, suppose you have a family of abelian varieties, this is exactly what you would do. You would parameterize the H1, the family of H1 of your abelian varieties, and D would be your Ziegler space, and gamma would be SP to GZ. Okay. So this is just a generalization of this standard construction when you look at moduli of complex abelian varieties. Except that there are a few interesting things in that case. So, and one has to be precise if we really want to say something interesting. So actually, what is this D? Well, actually, as I said, the only generic invariant of this family is the Mumford-Tate group outside of the Hodge locus. So as I said, outside of the Hodge locus, my Mumford-Tate group is locally constant. And so I get what I call the generic Mumford-Tate group GS. Okay. So if you think of the case of abelian varieties, the generic Mumford-Tate group will be the general symplectic group GSP2G. Okay. Now, what is D? Well, D can be completely described as simply a conjugacy class under the real points of that group. Namely, this is a conjugacy class of one Hodge structure factorizing through that group. So this is like the general formalism of Shimura varieties, but you have to do it more generally. And geometrically, what happens is that, like in the case of Shimura varieties, this flag domain DS is open inside a flag variety for the complex points of your group. Okay. And here in my description, gamma, I would just take GS of Z, an arithmetic group in G of R. So now the problem is that to a Hodge structure, you have associated such a map, and this map has to be holomorphic. The reason why it is holomorphic is that it's an old result of Griffiths, is that, and this is the way we have defined a variation of Hodge structure, is that the Hodge filtration varies holomorphically. So this is why the Hodge filtration is much better than the Hodge bigraduation, because it varies holomorphically. So you get a holomorphic period map, and okay, there was one more constraint in variation of Hodge structure, which was this transversality condition of Griffiths, that nabla F is shifted by 1. You lie in F bullet -1. And here in geometric terms, this means that there is a differential constraint on phi. The differential of that map has to map the tangent bundle to S to a very peculiar subbundle of the holomorphic tangent bundle to D mod gamma, which is called the horizontal tangent bundle. Okay. And what is the most interesting in that picture is that, of course, you get this subbundle, and this subbundle defines a non-integrable distribution. It's not stable under Lie bracket. Okay, so it's not a foliation theory. It's exactly the opposite. This is a completely non-integrable system. Okay. So this is the holomorphic description of what is a variation of a structure. And in fact, this is completely equivalent. So a period map will just be a holomorphic map from this analytic space to a guy of the form D mod gamma, which is horizontal. And if you have this, it's easy to see that actually you can reconstruct a variation of a structure out of that. So some points that I should emphasize is that for people used to moduli of abelian varieties, can think that everything here is almost trivial. I'm just generalizing, but actually abelian varieties are very special because you are working with a structure of weight 1. In the case of abelian varieties, D mod gamma will be a Shimura variety or a connected Shimura variety. In particular, it will be an algebraic variety. But in most cases, as soon as you are in weight at least 2, in most cases, this guy is absolutely not algebraic. By that, I mean that there does not exist a single algebraic structure on that quotient. And this is very important because this reflects the fact that Hodge theory is really transcendental. So even if you start from a family of algebraic varieties of a C, Hodge theory will give you, in general, just a holomorphic map, which has no algebraic properties because this D mod gamma has no algebraic structure. Okay, so now let's come back to our problem. Our problem was to understand the Hodge locus. So how do you relate the Hodge locus to that period map? Well, it's very simple. You see, we said that the Hodge locus is exactly the set of points in S where the Mumford-Tate group is not the generic one. So this means that inside D mod gamma, I will have a lot of copies of D prime mod gamma prime for subgroups G of G prime. Countably many, because my groups have to be defined over Q. So inside this quotient, this Hodge variety D mod gamma, there are countably many Hodge subvarieties. And then what will be the Hodge locus? It will just be the pullback of those Hodge subvarieties by this holomorphic period map. Okay. So what I'm saying is that each time you have a Hodge subvariety dy mod gamma y embedded inside ds mod gamma s, which is a strict closed complex analytic subvariety, you can just put it back into the period map, and it will give you a complex analytic subset y inside S. And this will be exactly one finitely many component of the Hodge locus. Okay. So what is really contained in Catanide-Kaplan theorem is the very surprising following fact that you start from dy mod gamma y, which is a complex analytic subvariety of ds mod gamma s. You put it back under this map, which is only complex analytic, and you get something algebraic, which is kind of crazy if you think of it, because there is absolutely no reason why this should be true. So here I made a picture. So you have this big space ds mod gamma s. Suppose for a second that your period map is an immersion. So S, essentially, I think of it as being a complex analytic subvariety of ds mod gamma s. And now inside ds mod gamma s, I have a lot of subvarieties of the form dy mod gamma y. And I look at the intersection of that thing with my s. This defines exactly my y. And y will be a special subvariety, one of the components of this Hodge locus. But what is remarkable is that this is algebraic. Are there any questions? So this is the basic pictures that you have to understand. You have a holomorphic map between the identification of an algebraic space to a Hodge variety, which is a purely holomorphic object. But this purely holomorphic object has a natural collection of sub-objects, those d prime mod gamma prime, and you can look at what happens when you pull back those guys. And the Catani-Delinka-Plan theorem tells you that, in fact, this pullback, this pre-image, is a finite union of irreducible algebraic subvarieties. Okay. And so an irreducible component of such a pre-image is exactly what I call the special subvariety. So why is this picture interesting? It's interesting because it interprets Hodge theory as an intersection problem. At least the theory of the Hodge locus, not the entire Hodge theory, but understanding the Hodge locus, this is really an intersection problem. You want to understand the intersection of the image of S in your period domain with those subvarieties D prime mod gamma prime. Okay. All right, so we will come back to that in not too long. And so what is the main question that I would like to address in that talk is the distribution of the special subvarieties. For instance, you have this countable union of special subvarieties, this Hodge locus. What can be the Zariski closure? Right, this is a natural question. You know that a countable union of irreducible subvarieties, and you take their union, and what is the Zariski closure of that? So in the rest of this talk, to be simple, so that the statements are not too sophisticated, I would assume that the generic Mumforted group of my variation is simple. Otherwise, you have product phenomena, and you have to be careful in the statements that you make. The results are essentially the same, but you have to be much more careful in what you say. So recently with Odvinovska, I proved the following. Okay, now you have this Hodge locus. And as I said, there are some components that I understand. These are the components where, this dy mod gamma y, where this the image of the special subvariety in d mod gamma is positive dimensional. This means that I can do some geometry, right? So that, I will distinguish two cases. Either this image here is positive dimensional, or it is a point. About the points, basically, I won't say anything. Okay. So this is the following definition. I will call the Hodge locus of positive period dimension. This is the union of the special subvariety with image under the period map are positive dimensional. So, for instance, there is no positive dimensional Hodge locus for the modular curve, just because it is a curve, right? I can have only points. But in the case of moduli of abelian varieties, I don't consider the CM points. I will just take the positive dimensional special subvarieties. Okay. All right. So what is the result that we prove with Odvinovska? It's kind of surprising. It tells you that if I take this locus of all the positive dimensional special subvariety, I take their union, then either it is itself on the nose algebraic, or it is Zariski dense. Okay. So there are no intermediate possibilities. A priori, if you're a countable union of stuff, Zariski closure could be more or less anything, right? But here we say this is not possible. At least if we restrict ourselves to the positive locus, you get only two possibilities. Either actually this union was already algebraic. So what does it mean? This means that when you take the positive dimensional special subvarieties, they are contained only in finitely many maximal ones. This is what it means. You can have countably many, but all of them will be contained in finitely many maximal ones. Or it is Zariski dense. And we know already that the case of Zariski density occurs, right? You just think of the case of moduli of abelian varieties. Then the locus where a complex abelian variety splits as a product of two non-trivial abelian varieties, this is already dense for the usual topology. Here, the conclusion is only about the Zariski density. And actually, a corollary of this theorem tells you something, even in the case of the moduli space of abelian varieties. So suppose you take closed irreducible variety space, and suppose it is Hodge, you take the intersection with the positive Hodge locus, with the Hodge locus of AG, with all the special subvariety in AG. Okay, and then you keep only the positive dimensional components. And then this result tells you that either you have only a finite union of special subvarieties of S, or you are already Zariski dense. So it was not known even for abelian varieties. Okay. So this was nice, this result, but the main problem is that it does not give me any intuition when is it finite union or when is it Zariski dense. So when we proved this, we did not have any criterion. Okay. So what I really want to discuss today is what can you prove? Especially, are there cases where this positive Hodge locus is actually algebraic? Okay. Okay, and actually, what is surprising is that we prove that generically this is the case. So all the examples that I've shown you, they are completely non-generic. So I will define a simple invariant of my variation of a structure, which is its level. So what is the level? Well, you take the Mumford-Tate group and you take its Lie algebra. Now, the Lie algebra is a representation of the Mumford-Tate group. And so each point in your domain D defines a Hodge structure on the Lie algebra. Okay. So what I will call the level will be the largest case such that the piece of type k minus k of the Lie algebra is non-zero. The Lie algebra has a Hodge structure of weight 0. So the Hodge decomposition is direct sum of gi minus I. And so I am just looking at the length of this Hodge decomposition, but for the Lie algebra. So what is interesting is to notice first that this is much more natural than just looking at the weight. It's more precise than looking at the weight of the variation. So the level will always be smaller or equal to the weight of the variation. But what is interesting is that this is much more natural. For instance, if you look at families of K3 surface, so you are looking at degree 2 cohomology. So this is weight 2. But nevertheless, it's well known that this is parameterized by a Shimura variety. So morally, this means that this is weight 1 because it comes from the Kugas-Atake construction. But here you see it immediately because if you look at the Mumford-Tate Lie algebra, then actually it is of Shimura type. So you have only G1 minus 1. Okay. So this is the level. And now what is the main theorem that I want to not explain because I won't have time, but at least to expose is this result with Baldi and Ulmo that if the level is at least 3, then actually this positive Hodge locus is algebraic, always. So I remind you that for this statement, I'm still assuming that G is simple. Otherwise, you have to be a bit more careful in the statement. So in other words, as soon as the level is at least 3, then there exist only finitely many maximal special subvarieties of positive dimension. So let me give a simple example. We come back to families of, but rather than taking families of surfaces, where it was not the case because I stated that the Hodge locus was dense. I take family of hypersurfaces of dimension at least 3. So let's take the universal family of hypersurfaces in Pn of degree. I think here this is a mistake. I think this is Pn plus 1. Yeah, this is Pn plus 1. Sorry for that. This is very important because otherwise n is sharp here. So here this is, you take so n is the dimension of the hypersurface, not of the ambient projective space, and of degree d. And then what I claim is that if n is at least 3 and d is at least 5, then the Hodge locus of positive dimension of that stuff is actually algebraic. And the reason is that you can easily compute that in that case, the level is at least 3. So this is very surprising. Not only the Catanide-Kaplan is true, telling you that this positive dimensional Hodge locus is a countable union, but actually all those components are contained in finitely many maximal ones. And so the Hodge locus is actually algebraic. Just a remark, I will not talk about that, but and not only this, but you can prove that this is defined over Q bar in that case. All right, so what I would like to explain is how such a strange condition comes up. How do you get to that? Well, the idea is, as I said, we come back to this description of the special subvarieties as intersections. So when you have an intersection, there are only two possibilities. Either it is typical in the sense that the dimension is the expected dimension, or it is not. It is atypical in the sense that the dimension is bigger than the expected one. Okay, and this is the basic idea. So the basic idea is really you take your special subvariety, so you know that you can write it as a preimage of complex analytic subvariety dy mod gamma y in d mod gamma as an irreducible component of that. Little zero means irreducible component. And so we say that it is atypical if it has bigger dimension than it should have. In other words, its codimension phi of y inside the period domain, the codimension with respect to phi of s, which is the ambient variety, is smaller than the dimension of the ambient space, which is d mod gamma, with the things you are intersecting with, which is dy mod gamma y. So maybe you have to contemplate a bit this if you are not. I'm just saying that forget about the phi, just think that everything is embedded inside d mod gamma. So S is the subvariety of d mod gamma, and you are intersecting with dy mod gamma y, and the intersection is y. So if you are in generic position, here you should have an equality because the codimension should be exactly equal. If you are atypical, this means that your codimension is of the intersection is actually smaller. You have an excess intersection, okay? And so this very basic remark tells you that the Hodge locus can be described as the disjoint union. You have the atypical guys on the one hand, and of course, because they are atypical, you expect them to be not so numerous, right? I mean, there should not be so many of them because these are, after all, these are atypical intersections. So this is atypical. And the other ones, which are the typical ones. Okay. So that's the basic idea. And now the main conjecture that I made a few years ago in a weaker form, so now we have a stronger form, is that actually when you look at this atypical Hodge locus, it is always algebraic. Okay. So really, you shouldn't have so many, and this part here should always be algebraic. So in the case of Shimura varieties, this conjecture is exactly what is called the Zilbert-Pink conjecture. So if you want the conjecture that I made, you can call it the Zilbert-Pink conjecture for variations of Hodge structures. Okay. And as a simple example of that conjecture, you get a generalization of the André-Hort conjecture, but now for general variation of Hodge structure, which tells you that if you take a variation of Hodge structures, even mixed if you want, here I'm exaggerating a bit, I explain only the pure theory, but you can do it in the mixed case. And you suppose that in the base, you have a Zariski-Denz set of CM points. And then the answer is that this should never happen, except if essentially your period domain is a Shimura variety, and the period map is dominant. Which is if you restrict yourself to the case where you already know that you start from something parameterized by a Shimura variety. This is exactly the André-Hort conjecture for Shimura varieties. Okay. So I don't think I have time to explain interesting examples of that conjecture because yeah, I'm already very late. So this is the first conjecture. The first conjecture tells you that the atypical locus is always algebraic. So the second conjecture tells you that, of course, you should contrast that with what happens for the typical locus. And the answer there is that the typical locus, well, it can happen that this is empty, but if it is not empty, then it is always analytically dense. Okay. And so now if you put those two conjectures together, and because the Hodge locus is the disjoint union of the typical and the atypical locus, you see that if the typical locus is empty, then actually, sorry, once more, this is a typo. If it is not empty, then the Hodge locus is actually analytically dense. And if it is empty, this is really a bad typo, then this Hodge locus has to be algebraic. So now at least you get a heuristic. Either you have only atypical intersection and then you are algebraic, or you have some typical one and then you are always dense. And this would explain my result with Odvinovska, okay? Good. So now what can we prove about those conjectures? So first, the first result that we prove about the atypical locus, well, basically we prove the geometric version. So as I said, we can't say anything about the atypical points, for instance, the CM points. But what you can say is that suppose that you consider the Hodge locus, which is atypical and of positive period dimensions. Okay, so the image in the period domain is not just a point. Now take the Zariski closure of that. Then the conjecture predicts that actually this Zariski closure is exactly that set. So an irreducible component of the Zariski closure should be a maximal atypical special subvariety. And we prove that if it is not the case, then actually we control exactly the geometric shape. And what happens is that if this is not the case, Z contains there exists a nice decomposition of a nice factorization of the period map to a product situation such that Z contains a Zariski dense set of atypical special subvarieties of 0 period dimension, essentially. So for this second period map. So in other words, if the conjecture is not true, this is again because of the bad of the special points, of the atypical special points that we are not able to understand. So the conjecture tells you that this part should not happen. Why? Well, because actually this Z has to be contained in someone which is special typical. That we managed to prove. So, I mean, this statement is a bit complicated, but you should just remember that we prove that either the conjecture is true or we really control what happens. And the bad things that could happen comes from atypical points. So the only things that we don't understand are the atypical points. So this is what you can prove about the atypical locus. So what about, now what is the main theorem? The main theorem is that if the level is at least 3, I mean, this is not the main, this is one of the main, but so the second theorem is that actually, if the level is at least 3, then the typical locus is empty. So here there is no mistake. Okay. And so this means that if the level is at least 3, the full Hodge locus is purely atypical. Now, if you put together what I said, you get the main theorem. Why? If the level is at least 3, then it tells you that the typical Hodge locus is empty. But now you look at the previous result, and it tells you that you create a special typical subvariety if you are in the alternative B. But you know that this special locus is empty. So B cannot occur. And so this means that actually Z has to be a maximal atypical special. So it tells you that the Hodge locus is purely algebraic. Okay. All right. So now I should give, because I won't have much time about this, I should give an idea. And this theorem too, what is remarkable is that this is purely Lie algebra theory. The idea is that because of the Griffiths transversality, if you want the the intersection to be typical, this means that you have to take into account all the non-horizontal direction. So this means that the guy, the Mumford group of the special subvariety you are looking at, it has to have at least all the pieces, all the non-horizontal pieces of the ambient Mumford group. But then from Hodge theory, you see that you would generate everything. So the only group satisfying that condition will be already the ambient group, and that's it. Well, and now what happens if the typical locus is not empty? Then we prove, so this means already by theorem 2 that we are necessarily in level 1 or 2, and then we prove that we are actually analytically dense. And this is not difficult, this is basic differential geometry actually. So what we still don't have is a complete characterization. What happens in level 1 or 2? So just to make a comment, all this is coherent with the examples that I showed you at the beginning, because everything was in level 1 or 2. Because people always look at that, because this is easier to describe. But this is really not the generic picture. This is what I'm trying to say, is that the giant picture is that this Hodge locus is very small. It is algebraic. Okay. So, so what misses, what we don't still have is a full characterization in level 1 or 2. When is this typical Hodge locus empty or not empty? So we have some examples. So suppose you are in level 1, so you start with a Shimura variety X mod gamma, and we suppose that we're in such a Shimura datum that actually there is a special curve. This is not true for all Shimura data, but there are many Shimura data where this is the case. For instance, AG, right? And suppose now that for your S, you take something relatively big, like an irreducible hypersurface. Then it's very easy to show that in that case, if you look at the Hodge locus of S, which is just the intersection of S with the Hodge locus in your Shimura data, and you look at the typical locus, then this is not, again, this should not be 0, but empty set. This is not the empty set, and so actually the Hodge locus is dense. So for hypersurfaces of Shimura variety which contain a special curve, then actually this Hodge locus is dense. This is the kind of statement we can prove, but we don't have a systematic classification here. All right, so what time? I wanted to explain a fun arithmetic application of this just to conclude the talk, to explain you what you can prove with this kind of techniques at the level of arithmetic. So this is about an old question of growth. So it's well known, it's an example of Mumford, is that there exists a principally polarized abundant variety of dimension 4, which have a trivial endomorphism ring, but which are not Hodge generic in A4. Right, so more specifically, the Mumford group is a certain Q form of GM cross SL2 to the 3 inside the GSP8. Okay, so these are called abundant varieties of Mumford type. So these correspond to special subvarieties in A4 which are not of Pell type. Okay, and then Gross asks, does there exist a curve of genus 4 such that the Jacobian is of Mumford type? So I think this is a question that Gross asked like something like 20 years ago, which is a funny question. And actually, as an easy corollary of what we prove, we can prove that there is actually a curve of a Q bar of genus 4, which is of Mumford type. And I did not give any proof, so let's try to give one proof at least in the talk. So, of course, you look at the locally closed immersion of the moduli space of curves in AG, right? So the image is the open Tori locus, and I will call TG the closure, so the closed Tori locus in AG. So now you have an easy count of dimension. So MG is of dimension 3G minus 3, and AG is of dimension GG plus 1 over 2. And what is well known is that this closed algebraic subvariety, the closed Tori locus, it is Hodge generic in AG if G is at least 3. So in other words, the generic Mumford group is GSP8. Now, what is interesting when G is equal to 4 is that this is a unique G such that this Tori locus is of codimension 1. So this is really hypersurface inside AG. Okay. So now, what do we want to understand? We want to prove that there exists a curve of Mumford type inside TG0. So this means that we have to prove that there exists a special subvariety of Mumford type intersecting TG0. Okay. So by Mumford, let's choose such a special curve, which has a required Mumford group. So this form of GM cross SL2 to the 3. And now you apply the previous theorem, this theorem here, where S now is my closed Tori locus, my irreducible hypersurface. And because the special subvarieties corresponding to this Q form of GM cross SL2 to the 3 are exactly curves, I'm exactly in the right situation anyway. And so what I get is that at least if I look at the closed Tori locus, then it will actually cut infinitely many Hecke translates of that Y. So this is not exactly what the theorem here is telling you, but this is how the proofs work. Is that you look at the intersection, maybe not with your given curve, but with all the Ecker translate, and you prove that you have sufficiently many. So this is what it tells you, is that the closed Taylor locus will cut infinitely many such Mumford curves. But now, because of the density, you know that all those intersections, they cannot occur inside the boundary, because otherwise this would not be dense in TG, right? So at least you have infinitely many such Ecker translates that would cut the interior. So this open Taylor locus, which is the guy we are interested in. Okay, so now let's Pn be a point in such an intersection. And because Pn is in Yn, what is the possible Mumford group of Pn? Well, you are on a curve, so either you get a CM point, or you get the generic Mumford group of that curve, which is exactly the guy we are interested in. So if we are in the second case, we win. So what could happen is that all the intersection points are CM points, but if they are all CM points, then you apply André-Hort for A4, and this would tell you that that the Taylor locus would be a special subvariety. But we already know that this is Hodge generic, so this is not the case, and that's it. So this is completely non-explicit, but nevertheless, it proves the existence. So it's kind of a funny application. Of course, this is not what I'm really interested in, but I think this is a nice, funny application of this business. Yeah, I'm already 2 minutes over, or maybe 1 minute over, so I think I will stop here.
Okay, thank you for a great talk.
Thank you.
Any questions? Maybe while everyone is thinking, I'll ask you a question. So in this last application, why is it, how do we know that what we get is over Q bar? Because everything was over C before that, right?
Oh yeah, but no, I agree. I mean, actually, we can easily, there is some rigidity phenomena that proves that actually what you get is over Q bar.
I see.
But yeah, everything that we did, yeah, that's right. But interestingly, yes, I should have come back to that. I have another paper where we prove that this component of maximal dimension of the Hodge locus, if you start of a situation where everything is defined over Q bar, then actually they are also defined over Q bar. So this means that in level 3, the Hodge locus is actually at least of positive dimension. We don't know for the points. I mean, knowing for the points, it's not so far from proving that Hodge classes are absolute Hodge. It's weaker, but it's already a good point in that direction. And that, of course, we can't prove, but actually, yeah.
Wait, sorry, can you just say that again? Like, why can't you prove Hodge classes are absolute Hodge?
No, what I'm saying is that there is a nice interpretation of this conjecture that Hodge classes are absolute Hodge only in terms of those Hodge loci. You have to be a bit more careful. Actually, you have to work not in the Hodge locus in the base, but the full Hodge locus in the total space of the Hodge bundle. And if you look at those statements, then the conjecture that Hodge classes are absolute Hodge, it's equivalent to proving that those Hodge loci in the full bundle, if you start from a situation where everything is defined over Q bar, actually those Hodge loci are defined over Q bar. And so what we prove with Urbanik and Odinovska is that this conjecture reduces actually to the case of special points. So you just have to prove the conjecture for the points because the geometry we know how to deal with. And so in particular in our paper, we prove that all the components of the Hodge locus of maximal dimension, but in the base, not in the full bundle, they are defined over Q bar.
Maybe I'll ask another sort of philosophical question. So you said that this notion of level for the Lie algebra of the Mumford group is more natural than the weight.
Yeah,
the-
because this is the moral that I would like to say is that, you see, I mean, in some sense, a variation of a structure, it's not really important. What is important is the tangent subcategories that it generates. And so this tangent category, it's entirely controlled by the Mumford group. And so what is most natural is to look at the only natural representation of the Mumford group, which is the adjoint one. And in some sense, this is the one which is really describing what happens for the deformations, because this period domain, this is the Lie algebra, which is controlling this horizontal tangent bundle and so on. And so this is really what plays a role. And I think this is clear because from that point of view, I mean, the case of K3 surfaces, it's very clear, right? You just get this group SOP2, and when you look at the Lie algebra, then you see that the weights that appear are exactly of type of Shimura type. So you don't have to ask why is that I'm in weight 2 and I get something of Abelian type. Okay, you can realize it more or less motivically, not exactly, but at least motivatedly in the sense of Yves, André, by this Kuga-Satake correspondence. But from that point of view, I don't care, actually. I mean, from
any other questions? This was a really nice talk. I mean, the results are very interesting. It's just it takes a lot of time probably to
yeah. So
digest.
I mean, I apologize. I didn't have time to explain. What I want to say, maybe I should just finish with one word, is that this theorem 3 for the typical locus, this is really a differential geometry. So this theorem 2, as I said, this is Lie algebra. I didn't say a word about this theorem 1, which is in some sense maybe the most important, about this atypical locus. And here this is functional transcendence. So the main tool is basically this result of Baker and Zimmerman about what is called the Axe-Chanuel conjecture for variations of a structure. But I just didn't have time. But just so that you get an idea of the proofs are really in different directions.
So theorem 2 and conjecture 3 give you what you want, but theorem 2 is sort of replacement for conjecture 3 in this argument, if I understand correctly.
Theorem 1.
Theorem 1 and conjecture.
Theorem 1 is a replacement for
two,
conjecture 1. Yeah, I'm sorry. Well, yeah, there is a discrepancy. Conjecture 2 should correspond to theorem 2, but actually it corresponds to theorem 3.
But one of the theorems together with one of the conjectures
Yeah.
give you what you
Yeah,
want,
exactly.
and the other theorem is the replacement for the conjecture.
Yeah, exactly. So the main guy which was not expected in this picture was that guy. Actually, in the first version of the paper, we did not realize the main result, which is that actually this typical Hodge locus is almost always non-existent.
Okay, let's thank Bruno for the beautiful talk.
Thank you.
Thank you.